This week I'm gonna talk to you about Markov chains. That's the topic we're on this week. And for this, let's just take the DNA sequence, and let's assume you have 4 nucleotides, ACGT, and each one of these have an equal probability of 1/4 of being in a sequence. Right, and let's just pick one randomly. Let's say I pick A with 1/4, then I pick again randomly and I pick C with the same probability, then I pick G, then I pick C. Every time with a 1/4, then I pick T, G, T. And if you notice something about the way I created this sequence, at every step of my elongation, I took a new nucleotide only with this probability. That addition didn't depend of anything else. I, for example, didn't think of what the sequence was to that point at all. The system only depended of this. It didn't depend at all of the sequence. Well, when the addition of a new nucleotide is completely independent, only dependent on the probability of its nucleotide, that's what's called a Markov chain of degree 0. And it's 0 because, again, adding a new nucleotide to the sequence doesn't depend of anything else except the probabilities for its nucleotide. But let's say that instead of that system, I have a different system in which I have A, C, G, and T, but this time I actually keep track of the previous nucleotide. So that means that, let's say I go from A to C with a probability, let's call that probability 0.1, and I go from C to A with a probability, and let's call that 0.2. Then I go from C to T again with a probability, and let's call that 0.15, and from T to C, just let's say it's 0.2, and from T to G, I go from 1.2 back from 0.15, let's say, and then from A to G, from G to A, 0.155, and from A to G, I go 0.2, let's say. Then now the only thing that I have is G to C, and I go from here to there from 1, 2, and back from 0.3. Same over here for this case, and in this case I go 0.2, and in this case I go 0.15, let's say. And then there's all the possibility also that you could go back to the same nucleotide, that if you're in this state, then you go back to the same state, and let's call that a probability of 0.15, C to 1, let's call it 0.2, C to T 0.15, let's say, and G to back to G 0.1, let's call it. So if you see in here, we have all the possibilities again, but this time when I'm gonna pick a new member of my sequence, that the probability depends on what state I was in the previous position. And let's start out, let's say my sequence starts out with A. But and then if it starts with A, notice that now that limits my options, because I can only go from A to C, let's say, with 1.1, from A to T with 0.15, from A to G with 0.2, and or I could go back to A for 1.15. So you see now the probabilities for the next nucleotide depend on this state. And just randomly, let's say I went from A to G, so now it's G. Now that I'm in G, the same situation happens. Now from G, I go to A with a probability of 0.15, back to G with 0.1, to C with 0.2, and I go to T with 0.15, let's say it's T. Now I'm in T. So from T, I could go back to A 0.2, back to C 0.2, G 0.2, or back to T with 0.15. Let's call it, it went back to T. So we did this, and so on and so forth, right? So you now see that the point in this diagram is that in order to add a new nucleotide to elongate the sequence, that is dependent of the previous position. So for example, adding a new nucleotide will come from this. It'll depend on the position that we are, this state T. Well, this is what's called a Markov chain of degree 1. One state. Notice that for this, I only have to look at what the previous state was. I don't have to look at for example, from T, I only look for the next nucleotide. I only look where the system can go from here. I don't care what it was one step before, right? So if you use this explanation from here to here, part of your homework as, for example, about the memoryless characteristic of the Markov chain, then in here you should have that explanation. One more thing is that this is what's called a transition diagram. A transition diagram. It tells you how you go from state to state and with what probabilities. Well, if you look at this, you could also do this. You could also say ACGT and ACGT, and you could now take these transitions and put it in this matrix. So for example, the probability of going from A to A is 0.15, the probability of going from A to C is 0.1, the probability of going from C to 8 is 0.2, the probability of going from C to C is 0.2, the probability of going, let's say, from A to G is 0.15, oh sorry, for 2.2, I'm sorry, and we'll go from T is 0.15, etc. Right? So you can actually create this matrix. Well, this is what's called a transition matrix. And turns out that because you have this matrix, a lot of properties of the Markov chains can be manipulated using linear algebra. So you can take the matrix, do some calculations in there, and it actually follows the properties of the Markov chains. If you're not that familiar with linear algebra, if you took linear algebra, or if you remember it, or it comes easy to you, that's perfect. Then you can just take that route. But if you didn't, and linear algebra is not your forte, and you find it difficult, then don't worry. You can always follow this without having to do the matrix operations. Of course, it'll be easier if you did do the matrix, but you don't have to know the linear algebra in order to understand this process. This is all I have for this segment right now. Hope this is helpful, and please give me some feedback on how this video turned out. Thank you.